please support them. 2 weeks from today, we have a presentation by Mike Poland from the USGS and the Yellowstone Volcano Observatory about what they're monitoring and what they're seeing in Yellowstone. So, real-time science right now in 2 weeks on Yellowstone. This is also the time of year to send your dues in to support us. We're all member supported, and everything we do, we count on you for your support. So thank you. I just want to again mention questions, go to John Heberger via the chat function, and Sam and Mike will answer them at the end of the presentation. It's my pleasure to introduce two friends who have done numerous talks from us. I'll start with Mike. Mike is well into the double digits in GJH talks. He is a board member, has personally organized our first overseas trip to Scotland, as well as subsequent overseas trips to New Zealand. And they were all absolutely amazing. And yes, I forgot, he also did Iceland as well. Mike earned his PhD from MIT in 1971 in solid state physics. He then had a career at General Electric for close to 30 years, where he published numerous, well over 100 papers, and as a result is a member of the IEEE, the Institute of Electrical and Electronics Engineers, the largest organization of its type in the world. Mike was actually the president of that organization. Since retiring, he has been learning geology and doing absolutely amazing astronomy work, which you will get to see as soon as I stop talking. So I'll skip to Sam. Sam grew up in Nevada, about 50 miles east of Tahoe, and got his bachelor's in physics and astronomy from Hampshire College, then went on to earn a master's and a PhD through the University of Wyoming. Sam has done a number of talks for us, and I'm very much looking forward to this one. Sam has been the founder and executive director of Wyoming Stargazing, which brings astronomy to not just the tourists, but also the locals here. They have incredible programs, and I urge you to check them out when Sam has telescopes set up. It's truly a treat. And so now I want to turn it over to Sam and Mike, and look forward to seeing and learning about our night sky tonight. Thank you.
Thank you, Mike, and thanks, Brent, for having us here, and all the other folks from the club and arranging this talk. It's great to be with you again. As I think Brett mentioned earlier, unfortunately, it is cloudy tonight. So we're not going to be doing a live virtual stargazing program, but we are going to be showing you some images that we took during a live virtual stargazing program just a few weeks ago. And then we'll also share some images that Mike has taken through his telescopes and processed in full color, which are pretty incredible. I'm sure some of you have already seen those. But before we get into sharing those pictures and kind of weaving together a story of the universe for you, I want to show you a little quick 2-minute introductory video about these virtual stargazing programs that we started to do almost a year ago now, at the beginning of the COVID pandemic. And so I'm going to share my screen and bring up this video. And it'll show you a little bit about the instruments that we normally use for these virtual stargazing programs. Here you go.
Hey everybody, Samuel Singer here, the founder and executive director of Wyoming Stargazing. I'm here with the vice president of the board of directors, Mike Adler, and we're here at his house and his incredible observatory. He's been helping us out doing some virtual stargazing programs using his telescopes in there. So we're going to go down and check it out.
The observatory is unusual because it's called a clamshell, and it totally opens. And so you can have more than one telescope in it. A normal observatory that you see in pictures has one telescope in the middle, but this one I can have 3 telescopes because it can be completely opened. So what we have here is the 20-inch telescope, and it's a bit of a monster. It weighs probably close to a couple hundred pounds. This is my second largest telescope, which I use mostly for visual use and also looking at the moon and the planets. This telescope is my smallest, but it's a very useful telescope because a lot of the objects in the sky, the deep space objects we look at, are quite large. And some of them are many times the size of the moon. And so you need a telescope like this to so you can see the full field of view.
Join us for virtual stargazing programs via Zoom on New Moon Fridays throughout the year.
All right, so we will be doing some more live virtual stargazing programs in the upcoming weeks. So you can check back on the Wyoming Stargazing website for information about when those programs are going to be happening. And so we do have Mike Adler with us here. Mike, thanks so much for joining me tonight for this presentation.
Okay, yeah, this is Mike Adler, and I'm sitting in my control room, which controls the observatory. So in the winter here, I can be inside and warm while my telescopes are outside and in the cold. And actually, you want them to be at the ambient temperature so that they're you don't have just problems with temperature changing overnight. Anyway, I'm going to show you. We're going to start out as if we were actually doing a virtual stargazing tonight, but we're going to show you images that we took a couple of weeks ago, but I'll show you what's involved. So the first screen I'm going to show here is the control screen for controlling the telescope. And so the telescopes, you saw all 3 of them. We typically use just the 20-inch telescope for these events. And the first object we're going to look at is the famous Orion Nebula, which is predominant in the sky right now. And it's something that you can actually see with your naked eye. So here's a sky view of the above us right now. And this yellow dot here is where the telescope is pointing at the moment, which is at a home position. I'm going to tell it to go to find M42, which is sitting over here. And now and this is real time. This is actually going to happen, but there's no point in actually doing anything, trying to take a picture because the sky is totally cloudy. But we'll act as if it isn't cloudy. And so I'm now going to tell the telescope to go over to that object, and you'll see the yellow dot moving on the screen. And so this is a complete computer-controlled telescope. All 3 of them are actually. And what it does is it really simplifies the process of finding these objects in the sky, because the telescope is aligned to the sky through a process I won't go into, but involves taking like 150 pictures, and the software figures out where the telescope is. And so in the future, when you want it to go to an object, like I'm asking it to go to M42, it knows where it is and it automatically moves. And so you actually see the telescope moving with the yellow dot. It was just pointing at the celestial North Pole, Polaris, and it's now coming down on the east side where M42 is right now. about 9 o'clock at night, it'll be almost directly overhead. Well, not overhead, but pointing due south. Right now, it's a bit on the east side of the sky. And so it'll just to be about down there. And once it gets there, the screen will just tell me that the telescope is not only aligned to M42, but it is actually tracking it. Now that'll happen here in about 5 seconds. And now the telescope is pointing, and now you see the screen changes and it says tracking at sidereal rate. Now I'm going to change the, show you a slightly different screen. I'm going to go to the screen that controls the actual camera. So there's a separate program, which is this one, which actually controls the cameras. And what happens is if I want to take a picture, now that the telescope is aligned, I can just do that. And what we typically do, and actually I'll do it, the telescope is actually connected, and the camera is on. And if I want to take a picture, I would just tell it how long I want to take it, and then just hit the start button, and it will actually take a picture. Now, this you're going to see a picture pop up here, but it's not going to be very interesting since it's pointing in a dark sky. But this is the process that we go through when we're doing these virtual stargazing. We're taking short pictures on the order, in this case, of 10 seconds, and that's about the average of. And you just saw the picture pop up. This other screen is when we're actually taking long time pictures, where I'm taking a picture that might be 30 minutes at a time. The telescope is tracking the object, so it's always there, but we have an additional tracking device, a separate camera that's focused on stars in the sky, and it results in minute changes to the location of the telescope to make sure that star, in this case, there it is, I did a couple of nights ago, that star is always exactly at the same spot. So when we have a finished picture, you don't see any blurring caused by the motion of the stars. So I'm going to, that's all I'm going to say about this at the moment. We're going to start by actually looking at that M42 image, which we took a couple of weeks ago. And so I'm going to stop sharing my screen and let Samuel take it from here.
Mike, thanks so much for that introduction. And before I get going, I did want to ask the hosts if it's okay with them if we take questions during the presentation. I do a lot of stargazing programs, and what makes it really interesting for me is all the questions that I get asked. That's what keeps it fresh and different each time. And so I'd be thrilled to field questions about the objects we're showing everybody throughout the program. So if that's okay with John, when questions pop up, feel free to find a good moment to interrupt me, and I'd love to respond to those questions as they come.
Why the indirect route when you moved the telescope there? It traveled a long ways.
Yes, it did, because in this case, it's a little complicated, but the type of mount this is called an Equatorial Mount, and it's either sitting on the west side of the mount of the pillar that the telescope is on, pointing east, or it's on the east side pointing west. And in this case, it was on the east side pointing west when we first saw it. But this object was on the east side, so I had to flip the telescope around so it was on the west side pointing east. So what you saw was that the telescope essentially what's called a flop. It was flopping over from one side to the other. And that's why it took so long. Normally, if you're just taking a look at pictures on the same side that the telescope happens to be on, it moves very directly right to it. But that's the reason for that long, circuitous path that has to, where the telescope actually goes right through the polar North Star and flops over to the other side.
Thank you.
Great question. Yeah, I was noticing the same thing, that telescope taking the long way around. All right, so we're going to get started. And the first image I want to show you is one that shows us the beginning of stellar evolution. And I want to tell you a little bit about the story of stellar evolution. So this is a great object to start with because this is where stars are born. So what we're looking at here is a picture of the Orion Nebula, as Mike mentioned earlier. It's an enormous cloud of gas and dust left over from a previous generation of stars that have burnt out and or exploded violently. And so this huge cloud, although it's primarily hydrogen gas, is seeded with all the other elements on the periodic table. And this gigantic cloud, which is probably somewhere between 25 to 75 times as large as the entire solar system, has undergone some kind of a shock wave, and it's collapsing in on itself. And so there are pockets in this big cloud that are becoming so hot and so dense that baby stars are popping into existence. Nuclear fusion is beginning in these areas, which are the cores of these baby stars. And so these little dots that you're seeing in the middle of this image here are the baby stars. Right here, in fact, the area that I'm moving around is called the trapezium. There are 4 stars in there, and they're believed to be some of the youngest stars that we can see in the Milky Way galaxy, only 10,000 years old, perhaps. And if you're a star and you exist for billions of years, 10,000 years is like seconds old. So these really are baby stars. And I want to bring up one of Mike's images of the Orion Nebula in full color to show you some more detail. And then if Mike has anything to add about the Orion Nebula or the image, Mike can chime in.
Yeah, so this is a true color picture of this nebula, but I can tell you that the constituents of this picture are a combination of emission from hydrogen. So that red color in the image is from hydrogen gas. So it's the stars, the bright stars that Samuel was talking about, are exciting the hydrogen and causing it to enter an excited energy state. And then the electrons and the higher energy state drop down into a lower energy state, and in the process of doing that, they emit light. And in the case of hydrogen, the dominant line is in the red, in the deep red. And so that's really what most of this color is. You'll also notice it's kind of a purple color to it. And as Samuel was saying, all the elements in the periodic table are here. But in this particular image, we're also seeing the effects of the oxygen gas. And so the oxygen emits in the blue-green area. And so it mixes with the red light and produces that kind of purple light that you see in the background. Now, I should also say that this picture, you're seeing a lot more detail than we were seeing in that 10-second picture that the previous one was. And this picture was probably on the order of about 10 hours of imaging, because the area up here is much dimmer than the areas down here. And the trick when you're taking these pictures is to somehow not to make this so bright where we were looking before that it's blown out and you don't see any detail at all. But also so you can see the detail in these darker areas. But this is one of the premier things in the night sky right now, is this Orion Nebula. I should also say that the nebula itself hasn't changed very much, and there are sketches of this that were done in the 1700s that look remarkably identical to what we're actually looking at the moment.
Thanks, Mike.
Go ahead.
Yeah. So I'll just add one more thing about this object before we move on to the next one. Mike and I both mentioned that It has all the elements on the periodic table. And even with large telescopes, we can only see new stars forming. With space telescopes, like the Hubble Space Telescope, we can actually see protoplanetary disks around those stars. So we can see the beginnings of new solar systems, of new planetary systems forming around some of the stars that are being born out of this nebula. So truly stellar recycling happening in real time in this nebula and in all the other similar stellar nurseries that we have in the Milky Way galaxy and in most big spiral galaxies that we see across the universe. But we'll get to that a little bit later. So baby stars being born out of the stuff of dead stars in this object. So now I'm going to bring up an image of some really, really old stars, that are at the other end of their existence. We're going to look at a globular cluster. So this globular cluster is in the constellation Pegasus, just setting on the western horizon now, whereas the Orion Nebula that we just looked at, as Mike mentioned, is rising in the east. And it'll be great to see for the next several months. This object, we only have a couple more weeks to be able to view it before it's down below the western horizon. But what you're looking at is a really tightly packed group of several 100,000 stars, ancient stars. These stars are between 10 to 12 billion years old, as opposed to just 10,000 years old, as are the ones we saw in the Orion Nebula a moment ago. So we think that these stars that form globular clusters are the original stars that formed after the Big Bang, the first generation of stars to form. And the reason we think that is that when we take a spectra of these stars, when we break up their light and into their constituent wavelengths, what we see are the traces of hydrogen, helium, but not a whole lot else. So they're what are called metal poor stars. To astronomers, everything other than hydrogen and helium is a metal. So very, very poor metallicity in these stars, which lets us know that they are truly ancient stars, that they're not stars that have been reformed out of the dead star stuff from a previous generation. These are the originals.
Yeah, I should just mention that the original material that formed at the Big Bang was hydrogen and helium and a little bit of lithium. So that's what, when you see stars that only have hydrogen and helium, you know they're very old stars, because that's all that was there to form the stars.
Yeah, exactly. Thanks for adding that. And I also want to give you a little perspective on how far we're looking away from the Earth with this image and the last one, which I forgot to do. The Orion Nebula is actually pretty close. The Orion Nebula is about 1,500 light years away. So 1 light year is actually the distance that light can travel in 1 year. Turns out that's about 6 trillion miles. Light travels at about 186,000 miles per second. So if you calculate that out for the full year, you get about 6 trillion miles. So that times 1,500 is the distance to the Orion Nebula. A hop, skip, and a jump, really. Pretty close in the cosmic scheme of things. This globular cluster is 30,000 light years away. And the reason it's so far away is because these globular clusters aren't in the plane of the Milky Way galaxy where most of the stars are found. These globular clusters actually hang out in the upper and lower halos of the galaxy. We think that they're there because they were actually independent objects at one point, and the gravity of the Milky Way actually brought them in to become part of the Milky Way some billions of years ago. But they reside in the upper and lower halos. So from where we are in the disk to where these globular clusters are up in the halos is anywhere between 20 to 30,000 light years away. So not only are these stars really old, they're also really far away from us, but still inside the Milky Way. Mike, did you want to add anything else about this one?
You might let's see. You could zoom this in a little bit more, right? If you
Yeah, I can.
go up to the plus sign up there. Yeah.
Yeah, my controls are hiding. I just have to hide those
Okay.
really quick here.
Well, yeah, I can't do it because it's on your screen.
I got it now.
There you go. Yeah.
Yeah.
So
Are you done with 2020 and all the baggage that came along with it? Ready for
And so we talked about how dense these stars are. The stars in the center of this cluster are at similar distances that the planets are in our solar system. So they're really tightly packed compared to the average distance between stars in the Milky Way galaxy. So it really is a tight pack of stars.
yeah, I guess I would add a little additional comment too. All these stars were formed most likely out of the same cloud of gas and dust. You know, all stars are formed out of clouds of gas and dust. And initially, these stars were formed mainly out of a cloud of hydrogen gas, which as stars are formed, that's what they first burn to create their energy. But as Samuel was saying, the stars near the center are so close together, they're about the size of our solar system in spacing. And the sun would not likely have been a member of a cloud, a group like these, because the planets would have never been able to be stably to exist without the interference of other stars. And so it's pretty clear that the sun was once, most likely was in a group of stars, but it wasn't a group of stars like this, where these are called a globular. They were in a group of stars that are much less populated. Maybe instead of having 100,000, there might be only 100. And sometime over the sun's life, it got split away from what was likely its siblings, and is now alone. It doesn't. We don't have some additional stars that are associated with the sun, so it got split off from its siblings. It takes about, during the objects in the Milky Way take about 250 million years to go around the Milky Way, and in the various journeys that the sun has made over the time that it has existed, it probably did get peeled off from its cluster of stars that was once formed with.
Mike, Mike, you mentioned that what was at the very beginning was gas and dust.
Well, in the very beginning, it was just gas.
Yeah, and I'm wondering, what is the dust if everything is just hydrogen and helium?
Well, that's what it was then, but it isn't, as Samuel was saying. Now there are elements in addition to, well, there's, for example, there's oxygen and sulfur gas, but there's also elements of these same atoms. So over the eons, the sun is a third generation star, and it in our solar system is made up of hundreds plus of elements, and those elements form various compounds, and some of those compounds are dust, what form the dust out there, but you also have the gas as well. But when the universe was first formed, there was no dust. It was just gas. It was, in fact, it was fundamental particles. But once the atoms formed, it formed hydrogen atoms and helium atoms and a little bit of lithium, and that's all there was. So there was no gas, there was no dust when these stars were formed. It was just the hydrogen gas. But then the stars, once the stars die, they do produce additional elements, and these elements then react and form other various compounds that form the dust.
So Mike, this is Mike Sure. I have a question. These stars, we're seeing the light from them was produced 30,000 years ago, but they're 12 billion years old. They're still mostly hydrogen and helium. In 12 billion years, why hasn't the nuclear synthesis progressed to heavier elements? In other words, why aren't they building elements
Yeah.
through iron,
Yeah.
which is the limit that you can do in nuclear synthesis in a star?
Right. Why aren't they? Well, the answer is they probably did, but those stars live a very short amount of time. The heavier stars are the ones that progress beyond the simple element, like the sun. A star the size of the sun will burn through, starts with hydrogen and is now burning, creating helium. And when all the hydrogen is gone, the helium will get compressed enough to actually form carbon. But once all the helium is gone, the sun, that's as far as the sun goes. But a star that's much heavier, say 10 times the mass of the sun, will form elements, as you said, all the way out to iron. But a star that is 10 times the mass of the sun lives 1,000 times less long. So all those old stars, all those stars are long gone. They've died, and they're not. You know, they've gone off and produced the dust that's we have in the universe and in our solar system.
And the other side of that are the really, really small stars. So really, really small stars burn through their fuel much, much more slowly. And they can actually exist for hundreds of billions or even trillions of years. So it's likely that most of the stars in these globular clusters are actually really, really small stars. And so they just haven't burned through all of their hydrogen fuel and helium fuel and reached those later stages in nucleosynthesis that you mentioned, Mike.
Yep. They'll live forever. Yeah.
Yeah.
Almost.
All right, so we've seen baby stars in the Orion Nebula and stars at the other end or close to the other end of their existence, these really, really old stars in this globular cluster. Now I want to show you a few different images of dying stars. So we'll start by looking at a couple images of dying stars similar to our sun. And then we'll look at an image of a dying star that's much, much larger than our sun, that ends its existence in a much more catastrophic way. But first, a dying sun-like star. I'll zoom in again here so we can see a little bit better. So this is the Ring Nebula, an object that mostly graces the sky during the summertime, but we caught a glimpse of it about a month ago, just before it was setting on the western horizon. So what you're looking at here is basically the corpse of a sun-like star. Technically, they're known as planetary nebula. It's a terrible name, but around 100 years ago, when astronomers were first finding these objects, they thought that they were planets forming because of their spherical-like shape. We now know that they're sun-like stars that are dying. So what you're seeing here in the very center, this tiny little blob of light, is the dead core of a sun-like star that we call a white dwarf. So it's a core of a sun-like star that's begun to cool off and is probably no larger than the size of the Earth. The rest of the star has been poofed out into space, and that's this big ring that you're seeing around it. So all the outer layers of the star have been ejected from the core and are moving out in every direction from the core. The size of this object is about 1 light year in diameter. So 6 trillion miles from edge to edge across this ring of gas and dust being expelled out into the space around it. This one's quite a bit closer to us than the globular cluster we just looked at. This object is just over 2,000 light years away, so just a little bit farther than the Great Orion Nebula. And so our sun right now is roughly middle age. So in another 3 billion years, it will run out of fuel, 3.5 billion years, give or take. and will become an object just like this. Our sun will become a planetary nebula. The outer layers will expand outwards past all the inner planets. And in fact, the outer atmosphere of the sun will expand past the orbit of Mercury, past the orbit of Venus, potentially all the way to the orbit of Earth, even farther than that, maybe. So we get cooked, and then eventually the outer layers continue to expand past the outer gas giant planets, and the entire solar system is rendered to this expanding gas cloud in space. So a lot to look forward to, but probably 3 to 3.5 billion light years away. 3 to 3.5 billion years away from happening. Mike, do you want to add anything about the Ring Nebula?
No. Well, do you have the additional picture of it, or we maybe not? We won't show it.
No, I've got it ready to go.
Okay, why don't you do that?
Yeah.
So this next picture is a 62-hour picture. So, and the reason, I mean, that previous one was 10 seconds or 15 seconds, so it's very brief. So why does it take that long? Well, one thing is that this particular picture is what is called a false color picture, and we're only looking, the light that I'm looking at, it is coming from through atomic filter. So I'm looking just at the light that is being produced by hydrogen atoms and oxygen atoms and sulfur atoms. And when you take a 60-hour picture of that, you can see these outer clouds that are made. And you'll notice the colors. The red is hydrogen. The blue color in the middle is from oxygen gas that is being, oxygen is emitting that light. And then you'll notice it's sort of on the outer edge here, it kind of has an orangish color, and that's because the sulfur is green in this image. And so you get red and green together and you get that sulfur, that orange color. The other thing is worth in the 60-hour picture, notice this other little feature up here. This is that's actually another galaxy that is some untold distance away. It might be, 60 million light years away from us. But it's interesting, it wasn't the feature that I was photographing, but there it is.
Thanks, Mike.
Yeah.
So I want to show you another type of dying star. This time it's going to be a star that was much, much larger than the sun. We don't know exactly how much larger, but at least 5 or 10 times larger than the sun.
Oh, yeah.
So this is the Crab Nebula, and it's a supernova remnant. So a very, very large star exploded just under 1,000 years ago, and catastrophically blew its outer layers out into space. The core of the star still remains. It's not a white dwarf star like in the planetary nebula that we just saw, but rather it's a neutron star. We can't see it in this image, but with other types of telescopes, we can actually see at least the indirect evidence of the neutron star spinning really rapidly in the center of this object. And so there's a star up in the sky right now that is due to become a supernova sometime soon, sometime between tomorrow and the next 100,000 years or so. So I'm talking about the star Beetlejuice, the upper star on the left-hand side of Orion's shoulder. It's a beautifully bright orangish star that's hard to miss in the upper left-hand corner of Orion. Beetlejuice is enormous. It's in the final stages of its existence. It's a red giant phase, and it will explode sometime soon and become a supernova remnant. Betelgeuse is so close to us, only 500 light years away, that when it explodes, its brightness will rival that of the full moon. And we'll see that instantaneously from the brightness that it is right now to that full brightness of that of the full moon when it goes supernova. And then it will gradually fade away over the following several weeks, eventually to become an object like this 1,000 years later or so. The reason we know when this object that we're showing you now exploded was because it was seen by Chinese astronomers as well as by the Anasazi people. There's an amazing cave painting, a pictograph in Chaco Canyon that has an image of a very bright star, of a crescent moon, and a hand pointing in the direction to look to find this star. And it's corroborated with records kept by the ancient Chinese in the year 1054 AD. So it's believed that, that this star exploded in that year, and this is the remnant of that stellar explosion from that time. This one's also up in the sky this time of year, just down to the left of Orion in the constellation Taurus. The Great Orion Nebula is a much, much brighter object to see in the sky, although even that one is not visible to the naked eye, like the star Betelgeuse is. You'll still need a pair of binoculars to find the Orion Nebula. This object is much harder to find. You really do need a telescope to find this object in the night sky. Mike, anything you want to add about the Crab Nebula?
Well, it's the other thing that's interesting about these supernovas is stars, even these big stars, take millions of years to form. But when they die in a time frame that is short even by our standards. I mean, this star will, when it went, and like when Beetlejuice goes, you'll actually see it flare up and then die off in the matter of weeks, and it'll change its brightness in hours. So I find that fascinating when you look at the time scales associated with so many of these cosmological events. That most of them are, occur on a time scale that's much longer, way longer than anything that we can experience. But these stars will actually, supernova, happen in a short time, even by our standards.
Thanks for adding that. Let me bring up the image that you processed, Mike, so we can see a little bit more detail in it.
Yeah, and there it is. Yeah, so this is also what's called a narrowband image. In other words, I'm just looking at the hydrogen and the oxygen and the sulfur emission. And again, the emission is occurring because the nearby stars are exciting the gas into a higher energy state, and they re-emit the light at a characteristic wavelength. The reason a lot of nebula pictures, and this is actually a nebula, are done in the narrowband is there's a lot more detail. You filter out a lot of the light, and you only see the light from these three elements, and there's a lot more detail that can be seen. And that's why in this image you're seeing a lot more detail than you saw in the previous one. Not to mention the fact that it's a longer exposure.
Thanks, Mike.
Yep.
I just want to do a time check with our hosts. Please remind me when we should be wrapping things up.
I think we have another 10 minutes easily, so we could look at a couple of more images. One question I would like to ask is the colors. Are they correlated to a specific element, and then are they consistent from photo to photo? In other words, if I look at blue in one photo and that corresponds to a certain element, is that the same in another photo?
Yeah, that's a good question. In the case of, when I say it's a true color image, the answer is yes, they're all the same. The color is that hydrogen. When we looked at M42, the Orion Nebula, that was from hydrogen gas. But these last two images, this one is actually closer to true color because I've assigned, it's considered a false color image, but I've assigned the red from hydrogen assigned the hydrogen gas as red, and the oxygen as blue. So this does come close to actually the real colors. But a lot of my images, a lot of the images that are done by the Hubble telescope, are what is done and it's called the Hubble palette. So you have to be told that it's in the Hubble palette, because in the Hubble palette, hydrogen is green and oxygen is still blue. But so the answer to your question is, you have to ask the question: is this a true color picture or not? If it's a narrowband picture, or atomic picture, what is the palette that the colors were actually used in? And once you understand that, then there's consistency in picture to picture. But they're done different ways. And part of it has to do with the science associated with it. There's a lot more science available in these atomic pictures, because you're seeing light from the various elements specifically, and you're not seeing the combination of light from so many different sources. So you can learn a lot more about what's actually going on in these various objects by looking at the through atomic filters.
Great question. So we'll show you a couple more objects, and then we'll wrap things up.
Probably want to do a galaxy, right, Samuel?
Yeah, absolutely.
Yeah. So but I'll leave it up to you.
All right, thanks. So everything we've shown you so far is actually inside the Milky Way galaxy, with the exception of that tiny, tiny little galaxy that Mike pointed out in the background of the picture of the Ring Nebula. But now we're going to show you an image of a completely separate galaxy. So far we've seen images of objects that are several thousand to several tens of thousands of light years away. The closest galaxy to the Milky Way is the Andromeda Galaxy, over 2 million light years away. We're going to pass by Andromeda and go to one of the next closest galaxies that's over 12.5 million light years away. And the reason I'm going to show you this galaxy, which you'll see in a minute, is you can actually see the spiral arms of this, and it's pretty spectacular. So this is a picture of Bodes Galaxy. And Bodes Galaxy, like I say, is about 12.5 million light years away in the constellation Ursa Major, Big Dipper. And it's this beautiful spiral galaxy that actually has a companion galaxy alongside it that you can't see in this image, called the Cigar Galaxy. And they actually share material with each other as they swing past each other over several 100 million years. But notice that the brightness in the very core of this galaxy. We now think that almost every large spiral galaxy in the universe has a supermassive black hole in its center. So you're not seeing the black hole, but you're seeing huge numbers of stars densely packed in the core, potentially some of which are falling in to the black hole. And then the big sweeping spiral arms that extend far away from the core. This galaxy is a little bit smaller than the Milky Way. The Milky Way galaxy is about 100,000 light years from edge to edge and has probably around 400 billion stars. This galaxy only has about 200 billion stars, and its diameter is probably only about 70,000 light years. So a little bit smaller than the Milky Way. Mike, do you want to add anything about this one?
I'll let you go to the color picture, and I'll talk about it there.
Great.
Is this galaxy younger or older than ours?
This one is actually believed to be a little bit younger. This one's believed to only be about 200 million years old, compared to more like 8 or 9 billion with the Milky Way.
Yeah, so this picture is, to answer your question, this is a true color picture. It's taken with regular filters. Yeah, I should mention my camera is a black and white camera, and you get the color information and the atomic element information by putting filters on it. So in this case, we're looking at the red. The colors here are a mix of emission from. In fact, let me just point out these bright red areas here. These bright areas are areas where hydrogen gas is being emitted, and they are probably areas where stars are being formed, and the stars are formed in these spiral arms, and those are areas of star formation in the galaxy. And the blue color here is probably not oxygen; it's just scattered light off of the dust in this galaxy. Let's see if there's anything else. The challenge of taking a picture like this is that, as Samuel was saying, the center is so much brighter than the outer edge, particularly this galaxy, and so it's a tricky thing. You have to do what is called nonlinear stretching to make sure you don't you capture detail in both the bright area in the center and the dimmer areas out in the outer rings. But this is a truly beautiful galaxy. Beautiful spiral arms. It's a classic spiral galaxy.
So Mike, two questions. Your color, you putting filters on. So basically the hydrogen, it's the frequency of the energy coming out that you know it's hydrogen. Is that how you know? And the filter just lets in that certain frequency of light?
Not in this picture, but yes, when I'm using those atomic filters, the light, that filter is 3 nanometers wide. And so it's only allowing light from that particular transition in the hydrogen atom out. Now this picture is taken with broadband red, green, and blue filters. So you're seeing a mix of light. The only reason I was pointing out the bright red dots is that is hydrogen, but I'm not using well, that's not quite true. Okay, I'm using, this is a combination of a true color image, where the bulk of the image here is true color through these red, green, and blue filters. But I'm also using the atomic hydrogen filter, and that I'm adding that color into it because that allows me to, allows you and me to see these bright red dots around here that show places where stars are being formed. I should also mention something about the stars that are in this image. All the stars you're seeing in this image are not in that galaxy. They're all in the Milky Way. And even the small stars are. The bright red areas are coming from the galaxy, but they're probably clusters. Maybe some of these clusters of could be 1,000, 100,000 stars that are close enough together. They look like actually stars, but they aren't. They're clusters of stars. Now, one image I just finished, which I will send out to some people, actually does resolve individual stars in the galaxy, but that's unusual. And typically, I don't have the resolution in my telescope to resolve stars in these faraway galaxies.
Mike, my second question.
Is there a database that catalogs all of these emitted colors so that if somebody is observing at a different time, they can actually find out whether there's been a change in some of the emissions, so that the gaseous or the atomic structures have altered in some fashion?
Yes, and that's spectroscopy, and so the observatories, the big observatories around the world, and going back 100 years or more, back into the days, that was one of the breakthroughs, was being able to split the light from the various stars and look actually at the spectra of the light coming from individual stars, and that data does exist, and people do look at its changes. Now, a lot of the changes, in many cases, are quite small, it's quite slow, but some of the Hubble images, for example, of M16, which is the galaxy we see, not a galaxy, but a nebula we see in the summer sky, they've actually seen changes in the last 14 years. So there are changes that occur even in the short term.
Thank you.
Hey, Mike, my second question was, one of you mentioned that the center of most of these galaxies is a dark black hole that you can't really see. What is, we talked about the life cycle of stars. Is there a life cycle for black holes?
That's a good question. The answer is yes. Black holes, the last things in our universe, the estimate is that eventually all the stars will run through all of their fuel, and they will just go dark. And even the white dwarfs will eventually, all these stars will eventually blink out. But all that will be left are black holes. But even the black holes don't live forever. They absorb, they actually give out, a black hole isn't totally black, and it does give out some radiation, very small amount, but enough that over trillions and trillions and trillions of years, I mean, I'm talking, probably orders of magnitude of trillions, hundreds and hundreds, that black holes will eventually disappear as well. Because you see, the black holes will stop growing once the stars around it, it's either gobbled them all up or they've died. And so black holes will eventually just be, they will be what they are. They won't get any bigger, but in fact, they will get smaller.
And they form in a couple of different ways, some of which we understand well, others we really don't. So in terms of stellar mass black holes, not the ones that we find at the center of galaxies, the supermassive black holes. Stellar mass black holes are formed by the collapsed cores of giant stars. So I talked about the neutron star in the center of the Crab Nebula. The core of a dead star of that size has the potential to actually collapse into a black hole. And you could end up with a black hole that's anywhere between 20 times to 100 times the mass of our sun. So that's a stellar mass black hole. These supermassive black holes are millions to billions of solar masses, absolutely huge. We don't totally know how they got that big. It's a bit of a mystery, but they certainly did because they're there. But somehow they were either formed by lots of other black holes merging together, or some other form of accretion that happened in ways that we don't totally understand. But that's a topic for another talk. I think that'd be a fun one, actually. I know we're out of time. I want to bring us back to where we started, actually. Mike mentioned these red star forming regions that we can see in Bodes Galaxy. Those are the same type of objects that we showed you at the very beginning in the Orion Nebula. The Orion Nebula is a star forming region within the Milky Way. And so now I want to end with one other image of an object in the same part of the sky as the Orion Nebula. There's another famous nebula right there called the Horsehead Nebula. We got a picture of that a few weeks ago, named because of the shape that it appears to make in the sky. You don't even have to be that creative to see this horse head here. Maybe more like a seahorse, but still nonetheless a horse head. And there's an ongoing challenge for amateur astronomers like myself to actually try to see this object through a telescope with just your eye. I never have, but it's one of my goals in stargazing out here in Wyoming, is to actually be able to see this object through a telescope without using a camera. But Mike has taken a beautiful image of it, so I'll bring that up and let him close out with a little bit of information about the Horsehead Nebula.
Yeah, so it's interesting. I'll just make a comment about that previous picture and this picture. You'll notice the scale is different. And the reason is that was taken with a 20-inch telescope. And this next picture is taken with my 6-inch telescope with a focal reducer. So this 20-inch telescope has got a focal length of about 35 100 millimeters. This was about 600 millimeter, no, 900 millimeter. So you're seeing, but what's interesting about this image is, well, you can see the nebula, the Horsehead itself, but you're also seeing this cloud of red. And this is a narrowband image. This is taken through an atomic filter. And what you're looking at is a tremendous amount of red, of hydrogen gas that is emitting. This is almost in monocolor. You can see some blue color mixed into it, and that's oxygen gas. But this is a narrowband image taken with hydrogen as in its natural red color. So we actually have never showed you one of the green ones in this talk. But anyway, this is a must-do picture if you're into astrophotography, is you have to do this. And I'm actually staking more of this winter. So far, it's been I haven't had that many clear nights, but I'm going back to the 20-inch telescope and I'm zooming in on this center part, and I'm doing it with broadband filters. So I want to make a composite image that'll have both light, that'll have elements of the broadband RGB as well as the narrowband together. This is another nebula over here. This is a different feature. It just happens to be right next to it. And this feature is called the Flame Nebula, and it's a mix of hydrogen and oxygen gas. That star, that bright star that's just to the left, that's the leftmost star in the Orion belt. Alnitak. Yeah, Alnitak. Anyway, so be it. Yeah, and these, of course, those of you who are into this, who might know that these constellations, like the Orion Constellation, are asterisms. These stars just happen to line up. They're not necessarily close to each other. The belt stars are in each a different plane. They're at a very different distance away from us. They just happen to line up into forming that nice belt, but they're not at the same distance from each other.
Hey, Mike, could you take a minute and kind of describe how on earth you make these images? I mean, you were talking about tens of hours and what all.
Yeah, I saw there was a question that someone asked, how can you take a 60-hour picture or whatever? This one is probably on the order of 10 hours. Yeah, so what it is you can't take a 10-hour picture, obviously, because the nights aren't that long, or, and these constellations disappear below the horizon. So this picture was taken with, I'm trying to remember, I think a sequence of 10-minute pictures, maybe 50 10-minute pictures through each filter. So since it's a black and white camera, I take a picture through, say, the hydrogen filter, and I might take, each one of them is only 10 minutes in length, but I might take 50 of them. And the point is that you take the image in as short of a time scale that's necessary, so you capture the detail in the brighter areas, so you don't want to blow them out, so to speak, and lose the detail. But then to get the detail in the darker areas, you just have to take lots of those 10-minute pictures. And then what you do is you stack them, you add them together, you average them, and if you take say 4 pictures of the same, you get twice the signal to noise. So the noise goes up, but the signal goes up twice as fast. So 4 times gives you twice the signal to noise. So that's why you keep on taking more and more the pictures, so you can expose the darker areas. And then if I'm taking it, that's through one filter, so the hydrogen filter. So I'm taking an additional 50 pictures through an oxygen filter. And then I stack all of them separately, and then I merge them together in a program like Photoshop to make the color picture that you're seeing here.
And I trust you just program this into your computer and go to sleep, right?
Well, yeah, as far as taking the raw images, I don't sit there all night doing this. In fact, I've been known to do what you just said, start the thing out and then go to sleep and maybe wake up at 5 in the morning and shut things down. Or sometimes I wake up after light, and of course a lot of the images are totally blown. They're it's daylight, but yeah, I just throw those away And yeah, that allows this process to be done, which isn't quite so painful as it would be back not too long ago when you didn't have these mounts that can track the motion of or the Earth's rotational motion so accurately that the stars aren't blurred. People used to have to sit there and adjust with their eye and to keep the star in the same location to get a long exposure. And of course, it wasn't done with digital filters or digital cameras. It was done with film. So it was. This has actually gotten a lot easier to do in the last 20 years than it has in times earlier than that. Like going back to the start of the 20th century, when there was a tremendous amount of activity just happening in astrophotography, and where Hubble got did his thing, and with help from this Henrietta Swan Leavitt, figured out the distance to these galaxies, like the one we just saw. The Andromeda was the one that was the breakthrough. He showed that it was millions of light years away and not in our Milky Way galaxy itself, which was what's called the Great Debate, where people debated the idea of, is this thing in the Milky Way, is the universe the Milky Way, or are these island universes, are they much further away? And then he answered, oh, there it is. Oh, there's the Andromeda. And Hubble looked at a star, it's called a Cepheid, that this Henrietta Swan Leavitt had figured out that the period of the variation of the light from these Cepheid variable stars is proportional to their brightness. And he was able to figure out that this object, this Andromeda Galaxy, was millions of light years away. He had it, his calibration was not accurate, but he had it right in that it wasn't anywhere close within the Milky Way zone boundary.
Say, Mike, Samuel, there are a couple of other questions that were posed in writing. So I'll ask these real quick, and if you could answer them. One was, when you were doing the mechanics of actually trying to get the telescopes to work, how do you know if something is east or west, and if you're coming from the North Pole?
Well, the automation in the mount does that for you, but the way in which, but the telescope itself has to be aligned, and Samuel has to do that every time he takes out one of his telescopes and set it up at night to look. He has to align the telescope to the stars. And you usually do about 3 or 4 stars. But when I'm doing it for this astrophotography, I'm taking the way it's done. I take there's an automated program in the Mount software where you take maybe 150 pictures, and this telescope is just all by itself shooting pictures and is moving and taking another picture. Then it puts all of these, does what a plane solve of all of these separate pictures, and figures out the orientation where the telescope is, and from that the program in the mount, which is the one that controls the telescope and does all the pointing, then allows you to just tell it where to go, and it does all of that all by itself. I don't have to tell it how to do any of that. It just does it.
Okay, another question, maybe a couple combined, is how can you take a picture for 62 hours since everything's in motion? And how many, sort of combined with that, how many actual pictures are you actually taking during that time and combining?
Well, I sort of partially answered that already, so I'll be real quick about it. In that 62-hour picture, there might be 250 pictures involved with doing that. Each one, and because of that one, I think the longest, those were 20-minute exposures. So it was maybe 100 images taken through each of 3 filters, and each of those 100 images is 20 minutes long by itself. So you can do the math. That's how you get to 60 hours.
Okay. how large is the Milky Way? I think you actually answered that, but maybe it didn't come through. And
I'll let Samuel handle that one.
and how much outside of the Milky Way can we actually see? And I'll presume that that question revolves around maybe with the naked eye or with binoculars, not with Hubble.
Yeah, good description there. So the Milky Way, about 100,000 light years from side to side. So I've got a picture up here of Andromeda. Andromeda is a larger galaxy than the Milky Way, but in a lot of textbooks, when you actually see a picture of the Milky Way, they'll show you a picture of Andromeda because we think they look fairly similar. But Andromeda is larger. If it was the Milky Way, from this side of the galaxy to the other side would be 100,000 light years. So each light year, remember, is 6 trillion miles. So 100,000 of those across the Milky Way. And if we could see it edge on, it'd be roughly 10,000 light years thick, bulging in the middle, maybe upwards of 30,000 light years, with the bulge at the top and the bottom, those upper and lower halos where the globular clusters are. And then in terms of number of stars, we think probably around 400 billion stars in the Milky Way galaxy. In Andromeda here, probably upwards of over 1 trillion stars. So the Milky Way is a slightly above average size galaxy, but still dwarfed by other larger galaxies out in the universe. Speaking of Andromeda, it's up in the sky right now. It's actually up in the sky most of the year. And it's the farthest object that we can see with the naked eye in the Northern Hemisphere. The Andromeda Galaxy is about 2.3 million light years away. And it looks just like a little gray smudge in the night sky on a moonless night. I was showing it to some guests a couple nights ago. And we could just barely make it out almost right at the zenith this time of year, the very top of the sky above our heads. So Andromeda is the farthest thing you can see with the naked eye. With a telescope like the size of Mike's, or the ones that we use with a 20-inch mirror, the farthest thing that we can see is the very closest quasar, the very closest quasi-stellar object, which is basically a supermassive black hole that outshines the rest of the galaxy that it's in the center of. That one is about 3 billion light years away. So we can just barely see this tiny little pinprick of light, 3 billion light years away with a 20-inch telescope on a perfectly moonless night.
Okay, there's a question about Beetlejuice and whether it will produce gravity waves that LIGO can measure. What elements will be produced by that event, and would it end up in a black hole?
Yeah, so Beetlejuice is large enough to potentially have its core collapse into a black hole. It meets the bare minimum cutoff for that, so it's a possibility. The core might stabilize as a neutron star, or it might become a black hole. We won't know until the core vanishes or not. So that'll be cool to wait for. During the supernova explosion, all of the elements on the periodic table, naturally occurring elements heavier than iron, can be produced. So all of the rare earth metals can be produced to some extent in those supernova explosions. We think that the majority of gold is actually made from merging neutron stars, but that's another story as well. But all those heavy elements, heavier than iron, can form from supernova explosions. Let's see, was there one other part to that question too?
Well, it was, I think I know the answer, but will LIGO be able to detect the gravity waves?
I don't think LIGO is sensitive enough to get gravity waves of supernovae. They are produced. Gravity waves are produced by supernovae, but I don't think LIGO is sensitive enough. I think the best that it can do are like merging neutron stars, which are much larger gravitational events than supernovae. But the next gravitational wave detector we build probably will be able to detect the gravitational waves of supernovae, but we're just not there yet.
Okay, and probably one last question, and that is probably more for Mike, and that is, do you photograph, observe light beyond the, what the spectrum that the human eye can see in any of your images?
Yes, I think so, because these narrowband filters do push the limits some, but even the hydrogen filter is still in the visible range, and so I don't make a point of my filters. My camera is not sensitive, into the deep ultraviolet or into the infrared. So I don't I don't have that kind of capability, but needless to say, the Hubble has cameras that are sensitive into the farther infrared, and the new Webb telescope, when it's launched in theory this year, is going to be particularly sensitive into the deep infrared, because it wants to look back farther in time. And the key to looking at objects that are going in farther in time is that all objects far away from us are moving away at increasing speeds, and so they get what is called redshifted into the deep infrared. And so the new Webb telescope will be capable of seeing objects further away and moving faster than Hubble will be able to. But I can't. I don't resolve any of that.
All right. Well, thanks for that. We're going to cut it off there. We want to thank both Mike Adler and Samuel Singer for a very most engrossing kind of program here. Probably every bit as good, even though the sky was cloudy. You guys did a great job of preparing a great show for this. Couple of things as we go forward. In 2 weeks' time, Mike Poland, who is the chief scientist for the Yellowstone Volcano Observatory from the United States Geological Survey, will give a talk on what's going on at Yellowstone. I think that's in 2 weeks' time. I think you'll find that very interesting. The Native Plants organization will have a program that we showed in the beginning. You can look at their website. That's on the 23rd Tuesday of February. So be sure and look that one up as well. And so let me just, I think, probably join everybody in offering a real round of applause to Mike and Samuel for a really wonderful program. So thank you, and thank everybody for participating tonight.
Thanks for having us.
2 weeks.
Yep, thanks a lot. We enjoy doing it. Yeah, join us. You all should, look when we have these actual virtual events real time on Friday nights. They're open to anyone in the community. So keep tuned to Wyoming Stargazing and pick those up when we have them.
All right. Thanks, everybody.